Right. All right, well, everybody, okay, cool. I think we're ready to go. So thanks to everybody that's joining us on YouTube and Zoom and, here in Westport, and the people that decided not to come out in this insanely cold night. So we thank you for joining us from wherever you're at. As we talked about a little bit earlier, we have the Westport Astronomical Society free science lecture series, and we've been doing these for years now. So Franco has been just fantastic at putting these great talks together. Thank you for that. And we've got so many more to come. As you know, every month we do this, and we hope that you can join us for more. And we always want to see you, if possible, to be right here in the classroom, because it's good to see everybody again, kind of mix and mingle and catch up on stuff, swap and tell some lies and tall tales and the usual stuff that we do here. So thank you for particularly the crowd that's in here tonight. Thank you for coming out in this. Tell you a little bit about our speaker tonight, because I've been just chomping at the bit to see this. And if you remember, we had him scheduled back at the end of last year, and then the government shutdown happened, so he had to reschedule. He couldn't do it, and understandably, we understand why. But it's great that we've got him rescheduled, that he's back, and that we could do this again. So thank you. And let me tell you a little bit about it. We're taking a fast tour through the James Webb Space Telescope as it's revealed, since its launch in December of 2021. It's discoveries that are already reshaping how we understand the universe. And we're pleased to welcome Naveen Vetcha to the Westport Astronomical Society's free lecture series. And this is for the first time. Dr. Vetcha leads the Aerosciences team at NASA's Marshall Space Flight Center and has worked directly on Webb's Sunshield, the RS-25 engines that power NASA's Space Launch System, and NASA's Centennial Challengers program. He's also an adjunct faculty member of the University of Alabama in Huntsville and an associate fellow of the American Institute of Aeronautics and Astronautics. In short, he's really hands-on with hardware and makes all these discoveries possible. And tonight, he'll guide us through Webb's journey so far. So please welcome Naveen Vetcha.
Hey, thank you. Thank you very much. I hope you all can see my screen properly. I'm working with a small computer, one screen, so I can't see what's going on in the Zoom. So, alert me if you need to stop me, because I can't see if somebody raises their hand. I'm using Zoom web version because NASA doesn't allow us to install Zoom on our computers. Okay. With that, I'm glad to be here and to be with fellow astronomers. All sky camera, get that. We installed that at One Brown Society here 2 years ago, and it has been working incredibly. And we are also planning for this weekend. We literally just talking this afternoon about canceling our public planetarium show this Saturday and running the faucets. We are not used to even 1 degree centigrade, which is not common here. So we are really freaked out about the possible mix of rain and snow. All right, with that, let's jump in. So Webb Space Telescope has been making science observations for about 3.5 years. Just in this short span, Webb provided us unprecedented views and details of various objects located as close as in our solar system to as far as the far reaches of observable universe. As our mothership, Earth, begins another orbit around the sun, this is a great way to start the new year by learning about the telescope and some major discoveries it made so far. I can't talk about Webb Space Telescope without mentioning the Hubble Space Telescope. As you can see, both these telescopes made it to the cover of Science magazine. Hubble has in so many ways completely revolutionized our understanding of the universe. It changed the way astronomers understand space, but even more than that, at a profound level, I think it changed the way that humanity thinks about space. Hubble Space Telescope, as you probably know, was named in honor of famous 20th century astronomer Dr. Edwin Hubble. And Webb Space Telescope is named after James E. Webb, second administrator of NASA, who led major NASA programs starting from Mercury, Gemini, and Apollo. There are a lot of other telescopes in the space, but most of them are designed to answer one or two specific questions. But Hubble was built to be as inclusive as possible. It was supposed to answer as many questions as you could think to ask, at least as far as the design allowed. And as we all have witnessed, Hubble succeeded splendidly. And it's continuing to send us great observations and will likely work well until 2030 or a little bit beyond that. But Hubble can tell us only about up to a certain extent due to its limitations. Mm, But to take us further, we need the Webb Space Telescope. We say that Webb Space Telescope is the successor of Hubble, and it definitely is. And I like to highlight some differences between Hubble and Webb to sort of understand what this telescope is like. So here is a infographic generated by ESA. On the left, you see Hubble information, and on the right, you see Webb. The first big difference is the size. Webb is big. This is by far the largest observatory we ever put in space, and the whole observatory is about 4 stories tall from bottom to top. Um, Pardon the use of metric system of units in this infographic. Where is the fun in a system that doesn't require me to know how many feet are in a mile, right? I will use US customary system of units in this talk so that we're all on the same page. One of the important things for a telescope is the size of the mirror. As you all know, Hubble's mirror is about 8 feet in diameter, and Webb's mirror is about 22 feet in diameter. As several of you in the room may already know, that there are two main reasons why the size of mirror matters. One, the larger the mirror, the more light it can gather. So it's like a light bucket. And two, the larger the mirror, the more fine detail it can get. So the images are sharper. The quality of the images that Hubble gets in Hubble gets and that Webb provides is going to be is same, because the quality is proportional to directly proportional to the size of the mirror, but inversely proportional to the wavelength. And we'll talk about wavelength in a bit. The second big difference between Hubble and Webb is where they are located in space. Hubble orbits the Earth about 350 miles in space, whereas Webb is located at a million miles from Earth, orbiting a point called L2, a Lagrange point, which is a gravitationally stable point in the Sun-Earth gravity system. And the third big difference is the wavelength in which they look at the universe. Hubble looks primarily in the visible part of the spectrum. It has some ultraviolet and some near infrared capability. Webb is primarily looking at the universe in the infrared part of the spectrum, and the reason for that is completely driven by the science mission, which we'll talk about in a few minutes. Let's look at this concept with more familiar objects. Uh, Here on the left, you have a picture of meerkats and a freshwater crocodile on the left in the visible light. Visible light usually provides us with detailed information about our environment, including colors and textures, as you can see on these meerkats and a freshwater crocodile. On the right, you have infrared, the same objects in the infrared light. In the infrared light, we see different details. The meerkats glow dramatically, and their high metabolism caused them to glow brightly in the infrared through the insulating layers of fur. And the freshwater crocodile is faintly brighter than the cool ground, which tells us it had recently been lounging in the nearby pool of warm water. It's been out of the water long enough to start to cool down. Um, so with our eyes, we can see external details like coloration, texture, and markings, etc. But with infrared light, it gives us very different but still valuable information, including temperature. The warmest areas glow brightest, and the cool areas like paws or the tips of scales appear darkest. It also makes clear that the meerkats on the left are much warmer than the crocodile, because the crocodile is cold blooded and the meerkats are warm blooded. In visible light, this difference between the two is not detectable. And we can't see infrared. It's redder than the red light. Everything is glowing, even if we can't see it with our eyes. Many things like computers, humans, benches, chairs, animals glow in infrared light. Here's some more information about the telescope. Telescope has two sides: observing side and sun facing side. The lower part of the Webb, where its five layered sun shield is, faces the sun. This is where its equipment that does not need to be cooled, like its solar panels, antennas, computer gyroscopes, and navigational jets are located. Its tennis court size sun shield protects Webb from external sources of light and heat, which ensures it can detect faint infrared light from very, very distant objects. But it's very important for its observing side to be very, very cold. And this is where all the instruments are. Webb's science instruments are housed behind this mirror, the primary mirror, separated by the sun shield from the warm communication and the control technology located on this side. Webb needs both passive and active cooling. Its five-layered sun shield provides passive cooling, so rejecting all the heat and light using radiation. And this first layer, we call this one sun-facing first layer, and the layer that is close to the primary mirror is the layer 5. The first layer is about 2 thousandths of an inch thick, while other four layers are only 1 thousandths of an inch thick. And here are some pictures from my team. I supported this building of these sun shields and um, validating some finite element models here in Huntsville. We're a subcontractor for Northrop Grumman called Nexolve, mainly building it and then deploying it in a clean room like the one shown on the top left. We use lasers like shown here to measure the shape of this layer, and we use a finite element model to predict the shape, and we compare the model prediction with the test data. And the requirement was, if we average out the differences between the model and the test data over the entire span of this tennis court, it needs to be less than 3/4 of an inch. We never had to go that high, actually. We rarely went beyond 3/10 of an inch. So most of the time it's less than 3/10 of an inch. And that's how accurate the models are. So that kind of builds our confidence in the model so that we can predict the shape in the in the space. And when we delivered the final layer, we were featured in a NASA article here. And this is the only picture they allowed us to take with our team in this clean room. They were very, very particular about the cleanliness. And as you can see, there are three technicians standing here at the center of the sun shield. I think this is let's see, this is layer 5. um, this is, I think, layer 1. This is very big. Layer 1 is biggest, but we delivered the layer 1 last. This is the last layer we delivered. And then we usually use to ship them in these crates like this from Huntsville, Alabama to Los Angeles, where the entire telescope is being integrated. And these truck drivers used to drive nonstop and actually reach Los Angeles within like 48 hours, again, because of any contamination concerns. So it's a fun work. All right, so here is a detailed view of Webb's instruments. There are three instruments operating in near infrared. and one in mid-infrared. NIR stands for near infrared, MIR is mid-infrared. And each instrument is like a Swiss Army knife of more specialized components with multiple ways of observing. Although some instruments are more suitable than others for observing specific types of targets, all four can be used for investigations of a wide variety of objects that make up the universe, including planets, stars, nebulas, galaxies, and etc. So teams working on Webb designed several innovative and powerful new technologies. We never put such a big telescope in space, and that too with a deployable sunshield. Um, Webb has specialized optics to align its mirrors to individually control each segment of the mirror, detectors that can capture and separate light from hundreds of sources at once, and custom thermocontrol systems. Engineers who created these technologies made Webb the most sophisticated and complex space telescope ever launched, and their diligent and hard work was easy to spot when Webb was in space. And as there are no rockets that have big enough payload volume to launch Webb as is, the telescope needed to be folded to fit in and was deployed once it was in space. There were 344 single point failures, with the 295 of which are associated with the deployment. So only Doctor Who could have guessed how many ways it could have gone wrong. But as all of you know, everything went really well, and it was successfully deployed and has been working fantastically. And the mission operations are conducted by Space Telescope Science Institute, located in Baltimore, Maryland. And engineers in flight control branch send commands to the telescope, monitor its health, and ensure observations are carried out as planned. All communications are routed through NASA's Deep Space Network, which has stations located in Australia, Spain, and California. And Webb can, I think, downlink at least about 58 gigabytes of recorded science data each day, and with a maximum data rate of 28 or 30 megabits per second or so. So let's see why Webb is designed to look at the universe in infrared. We talked about infrared a little bit ago. So by specializing in infrared, Webb will be able to see what's behind the dust we see everywhere in the universe. Here is an image of Cat's Paw Nebula, captured by the European Southern Observatory in the visible light on the left, and near infrared light in the middle, and the Spitzer Space Telescope in the mid infrared light on the right side. So, like Spitzer, Webb will be able to see through the dust in the regions like this, but at a very high resolution. In visible light, the stars that are forming in this region are inside these dense clouds of gas and dust, which scatters and effectively blocks their visible light from reaching the telescope. Near infrared light, it shines through all but the densest dust, revealing a lot of stars, all these blue whitish dots. And then mid infrared light shows gas and dust that glow with heat from the stars in these surroundings. So here is a same Cat's Paw Nebula as observed by Webb. Of course, Webb's view reveals a chaotic scene still in development, and you can see a lot of stars that are forming here and carving away the nearby gas and dust with these jets. Um, and this bright starlight is producing this bright nebulous glow in blue. So this is just a chapter in this region's large story that astronomers are putting it together, understanding. Here is another reason why Webb is specialized for infrared, to capture light that's traveled more than 13 billion years to reach us in our corner of the universe, from when the universe was only hundreds of millions of years old. We need a telescope that focuses on gathering a light that has stretched or redshifted over time to into the infrared light. Webb's sensitivity to infrared light allows us to see this ancient light of the first galaxies, which has been redshifted as it travels towards Earth over billions of years. So, if early on in the universe's expansion, light from stars that emitted in the ultraviolet and visible light due to the expansion of the universe that got stretched into longer wavelengths of infrared light. So, if you want to look for those early on galaxies, you have to look at the universe in the infrared part of the spectrum. We all like the great images that you all were looking, taken by your astrophotographers in your uh, club. uh, Even general public, whenever we think about space or astronomy, images of stars and galaxies probably pop up into your head. Images leave lasting impressions, but professional astronomers, astrophysicists, they have another tool called light spectra they use all the time. It involves spreading out the light to see what's in it. So spectra spreads out light from objects near and far, like the distant galaxy shown here, this like very tiny red dot in this image. And they spread that light out along the wavelength and plotted it, the intensity of that light. So it reveals what's in it, how far away it is, and how fast it is moving, all those details just from this simple spectra. All molecules and elements leave specific signatures, just like how each one of us have different fingerprint. Each molecule element has its own fingerprint, and that fingerprint is revealed when it interacts with the light. And we all know those well-known patterns of which molecule has which fingerprint. So Webb's near infrared spectrum here shows the graph has these tall peaks. These are emission features caused when specific wavelength of light are emitted by gases like oxygen, hydrogen, neon. So that tells us this galaxy has those molecules or elements in it. Just this is just to show you what usually astrophysicists use to identify the elements in an object, elemental composition of an object. All right, so we are going to get into some of the images. It's important to understand that Webb's cameras are far more sensitive than those on our smartphones. Plus, Webb doesn't instantly return full color images. Instead, imaging specialists at Space Telescope Science Institute that I mentioned carefully process these telescopes full color images. Every Webb image starts out as an unrefined black and white image like the one you see on the left. When any of Webb's raw images are initially opened, they appear almost totally black. This doesn't mean they contain no information. Instead, imaging specialists stretch or rescale these images, like the one shown at the center, to identify the bulk of the information that was captured within that particular filter. And then they can use multiple filters and then arrange them, combine them to finally come up with this colored image that we can see in the visible light. Here are the science goals of Webb. So Webb is actually taking new images and spectra. There is so much in the universe it will examine. Webb will capture light from the first generation of galaxies in the early universe and help us map how galaxies change over time. It will teach us about how stars form, live, and die, the entire birth to the entire life cycle of stars. Webb will find and explore the atmospheres of distant worlds called exoplanets. It will also observe outer planets in our own solar system, along with their moons. Webb will also study small bodies across a solar system, including asteroids, comets, and Kuiper belt objects. Plus, the telescope will also observe black holes near and far, including our own Milky Way's supermassive black hole, Sagittarius A star. So it's only been little bit longer than 3 years since Space Telescope's first full color images and data were released back in 2022 June timeframe. So what has Webb shown us so far? Let's take a tour together. These are some of the images which kind of my favorites. Everyone have their own. So I'll start from the solar system and go beyond and far away. All right, so let's start with the king of planets, Jupiter. Jupiter's magnetosphere has intrigued researchers for decades, and even now there are a lot of PhD students that uh, do their thesis research on Jupiter's magnetosphere. So polar auroras can help us understand the behavior of this magnetosphere further, and Webb's sensitivity allows astronomers to capture these fast varying auroral features. And they saw its auroras pop and phase changing on timescales of minutes to even seconds. The observations will help develop scientists' understanding of how Jupiter's upper atmosphere is heated and cooled. And a lot of these images and information is being processed and released, but the science outcomes of that data and images may take some time because they still have to analyze and understand and compare with their models and all that. So some of these images are out there, but it may not have yet resulted in a big discovery because it's still being analyzed. Um, so using this is the planet Doug or Uranus. Using the latest observations of Uranus, scientists identified a previously unknown moon orbiting the planet. So now I think Uranus has about 29 moons. And this newly discovered moon is estimated to be about 6 miles in diameter. So very, very tiny moon. And maybe that's why it was invisible to other telescopes and even to Voyager 2 back in the 70s. So it's a cool discovery in our solar system. And various telescopes collaborate often to get a full picture of certain features, yeah, on objects. Here is such an example. One on the left, you see an image of Neptune captured by Hubble. On the right, you see a combined image of Neptune from Hubble and Webb. And there is sign splotches which represent auroral activity, and white clouds are data from Webb's near infrared spectrograph. So Webb's detection of these auroras on the Neptune is the first time we have captured direct evidence of auroral activity on this planet. And as you can see, Neptune's auroras don't occur at the northern and southern poles of the planet, where we see auroras on planets like Earth and Jupiter, because of the strange nature of Neptune's magnetic field, which is tilted about 47 degrees from the rotational axis. And the Webb's study of this Neptune also revealed that the planet's upper atmosphere has cooled by several hundred degrees, likely the reason that Neptune's auroras have remained undetected for so long. So auroras remind me of yesterday's opportunity here in Alabama, that we had an opportunity to see very weak auroral phenomena, which is very, very rare. I hope you all got to see a better aurora last night. All right, moving to exoplanets, planets that are not in our solar system. Here is an artist's concept of a planet that orbits a sun-like star roughly 244 light years from Earth in constellation Lepus. In terms of size, mass, and density, this planet is between Earth and Neptune. Um, so this planet's orbit star that this planet orbits the star extremely closely, about like 5% of the distance between Earth and Sun, and it has an average temperature of I don't know 1300 Fahrenheit or so, which is how it feels in Alabama in the peak summer. Spectroscopic observations of planets' atmosphere show strong evidence of water, sulfur dioxide, and carbon monoxide, as you can see in this spectrum. So, of course, spectra like this will help improve planet formation models. And now, what can be the material content of this? If the planet is of this size, what can be the material content? If the planet is this far from the host star, what can be the material contents of its atmosphere and all that? All right, let's go even further. So here there are actually two stars that are forming in proximity, about 650 light years away from us. And those two newly forming stars are responsible for this scene that we see, like a hourglass shape, and the two stars are located in the center. And over tens of thousands of years, these central protostars have periodically ejected some of the gas and dust over time, and chemical reactions within those ejections and the surrounding cloud have produced a range of molecules: carbon monoxide, methanol, several other organic compounds. And all these symmetries and asymmetries in these clouds may eventually be explained as researchers reconstruct the history of this uh, pair of stars formation by updating their models to produce the same effects. And they're also astronomers are also eventually interested in how much material the stars have expelled, which molecules were created when materials smash it together, and how dense each area is. So let's look at a dying star. Depending on the mass of a star, some stars gently shed their layers during the later stages of their life. Stars at this stage were wrongly named. As you all know, planetary nebula. It's a misnomer, but we continue to use that name to refer to them. Here is the image of that a planetary nebula located about 1500 light years away. On the left is the image taken by NASA's WISE, Wide Field Infrared Surveyor Explorer, and on the right is a more refined image from Webb. So with this kind of detail, this helps understanding the turbulent nature of the later stages of the star, again, to accurately develop models or improve the models of life cycle of stars. I mentioned about Webb observing the supermassive black hole at the center of Milky Way, Sagittarius A star, and there is so much going on at the center of our own galaxy. This is the most extreme environment close to us, and all the researchers like to point every telescope towards it, so that all the current theories of star formation can be put to their most rigorous test. It's the bigger image shown here is captured by a radio telescope, um, and it's about 1,000 light years from left to right. Webb was pointed in a nearby star forming region here named Sagittarius C. It's located about 300 light years from the supermassive black hole. And Webb's data revealed never before seen features astronomers have yet to explain. An estimated 500,000 stars are seen in this image, shown in this small portion here on the top right. So here is an image of a region named NGC 346, a massive star cluster in the small Magellanic Cloud, which is a dwarf galaxy next to our Milky Way. And for whatever reason, there aren't many elements heavier than hydrogen and helium in this region, and that works in our favor because this region serves as a proxy, nearby proxy for studying the stellar environments with similar conditions in the very early and distant universe. And these yellow circles are the stars that were studied by Webb. And on the right, you see the spectra of one such uh, star. This yellow is the spectra of star and the surrounding environment and contains fingerprints of hot atomic helium, cold molecular hydrogen, and hot atomic hydrogen. Spectra of just the surrounding environment is shown here on the top in magenta, and it lacks the spectral line of cold molecular hydrogen. So the presence of cold molecular hydrogen confirms the existence of circumstellar disk around the star. That's where the planets will eventually form. So these findings indicate that planet formation around low metallicity stars, um, that's prevalent in the early universe, occurs over significantly longer time scales, like 20 to 30 million years, than what astronomers were previously thinking about, like approximately 2 million years. It takes about 2 million years for planets to form around a low metallicity stars. But with these observations, they concluded that it takes at least an order of magnitude longer than that. So, time to update their planet formation models. Let's move to a faraway galaxy. Here is an image of Sombrero Galaxy taken by Webb's near and mid infrared instruments. This galaxy is located about 30 million light years away. The near infrared image on the left shows where dust from the outer ring blocks the stellar light from the inner portions of the galaxy. Then in the mid infrared image, this actually shows this galaxy, like this dust glowing everywhere. And the interesting thing about what astronomers told about this galaxy is that they think this galaxy went through a merger with at least one other galaxy. The way they found out that is, this is home to about 2,000 globular clusters, just like in our Milky Way. There are like hundreds of globular clusters, which are collection of hundreds of thousands of old stars held together by gravity. And it's usually thought that stars in the globular cluster should have same spectra because they all formed from the same material around the same time. But the spectroscopic studies of stars within these globular clusters in this galaxy are unexpectedly different from one another, leading researchers to believe that a merger of two different galaxies over billions of years would have resulted in the current state of this galaxy. Here are two views of overlapping spiral galaxies taken by Hubble on the left and Webb on the right. In Hubble's image, the star-filled spiral arms glow brightly in blue, and the galaxy's core is in orange. Both galaxies are covered in dark brown dust lanes shown all over here. Whereas in Webb's image, cold dust takes the center stage, especially it's mid-infrared. So casting these galaxies are arms in white, where stars that are deeply embedded in the dust, they appear as pink. So a few billion years from now, these two galaxies will merge into a single massive galaxy. There's like a somber galaxy. So Webb took number of pictures of nearby galaxies. This is a collection of 19 face-on spiral galaxies. As the observing time on the Webb is very limited, it continues to take as many images. Not a day goes by without hearing a big news or a discovery from Webb. The Webb telescope discovered this incredibly distant galaxy, very hot off the press, in the fall 2025. Uh, this galaxy was observed to exist only 280 million years after the Big Bang, perplexing the researchers as they were not expecting such a matured galaxy that early in the evolution of the universe. So
Hey,
the
Naveen?
figure, yes.
Yeah, we had a little glitch with Zoom. Can you stop sharing and reshare again?
Oh,
We're not getting your
Yeah,
phone.
we see your name. So I think if you just stop sharing and share again.
what about now?
Oh, okay, then.
Okay, I'll do it again. Stop sharing. Share screen. What about now?
Yep, that's good.
Okay, I was talking about this exciting discovery back in fall 2025. So this is an incredibly distant galaxy observed to exist only 280 million years after the Big Bang, and scientists were not expecting an, a galaxy, a fully formed galaxy that early in the universe. So the figure on the right shows the near infrared camera, and bottom the near infrared spectra. And as you can see on the top here, this object is completely invisible at wavelengths 1.5 microns and below. So its light got stretched by the expansion of the universe. And then in the spectra, you see various ionized atoms, including nitrogen, carbon, and oxygen. So, in addition to the primordial signs of hydrogen and helium. So, very, very exciting discovery. I think this is probably a researcher down the alley from you, from MIT. They submitted a Mirage or Miracle Survey grant, I think, and it's got approved. So very, very exciting discovery. So prior to Webb's launch, only a handful of supernova had been found that occurred when the universe was only 3.3 billion years old. So that's about quarter of its current age. However, when researchers looked at the deep field images or spectra captured by the Webb, they found tens of supernova that occurred when the universe was less than 2 billion years old. So this image shows 80 such supernova in a patch of sky only about the thickness of a grain of rice held at arm's length. So a lot of heavy elements are created during supernova process. Understanding supernova explosions in the early universe is important to understand how heavier elements are distributed in the universe. So that's my favorite images in the last 3.5 years, starting from our solar system all the way to the early universe. So I hope you are all following Webb's journey. It's, even though I mentioned 3.5 years, just span of 3.5 years. The mission, Webb's mission was supposed to be 5 years, but we all know it's probably going to go on for at least 2 decades, the way it has been operating and the precision with which it was launched and everything went well, conserving a lot of fuel. So we have a lot of reserve left for station keeping. So hopefully, and unless some unexpected rock hits it, I think we have pretty good chance that we will have it at least for another 17 years, operating for another 17 years. With that, I can take any questions or any discussion.
Yeah, we've got, I don't know if Alex is going to be on this one, but we did have a question from, who is it? Steve Schreier. He's in Kalamazoo, Michigan. He was asking, what is the condition of the mirrors? And is there going to be, well, obviously, has there been any further micrometeoroid damage? Thank you.
Well, condition of mirrors right now is, I mean, I think they are working very well. The only unexpected strike happened before it commenced its actual science mission, but they kind of recovered from that. But they tested these mirrors by shooting like sand, very, very tiny sand particles into it. I think that happened here in Auburn or University of Alabama somewhere. So they're very confident at certain sizes, certain velocities, certain angles of tiny rocks, meteorites hitting it. So pretty confident about mirrors surviving for long term. I hope that answers.
Yeah. Let me, I've got the mic, so he won't be able to hear you unless I come over here to you. Hello, Gina.
Hello. I have a super basic question. Since the photos are in infrared, what do the colors represent? Like you show the pillars of Hercules and there's red and blue, but it's not really red and blue because it's infrared. So what are they? Are they the temperature? Are they the shift? Like what?
It depends on what we are looking in that image. Sometimes they want to explain the elemental composition. Then they assign different colors to oxygen, nitrogen, all those. So if it is about showing the temperature differences in the region, they will again show them as different colors. Typically, mid-infrared, if they combine both near and mid-infrared, near infrared is hotter, mid-infrared is cooler in that region. So reddish is near infrared, a little bit whitish is mid-infrared. So there is no one single way to explain the coloring in images. You have to read the caption and what they're trying to explain, depending on what information they want to show in that image.
Simple question.
Anybody else? Anybody else have some questions? Is there anything on Zoom, Alex?
I think this will be helpful.
Thank you.
Oh, yeah, Claire has one. Here you go, Claire.
Hi, I'm wondering what your personal level of interest is in the search for extraterrestrial life and how you think the James Webb, impacts that search. Oh, wait a minute.
He was too stunned with the question.
Yeah.
You killed him. I'm sorry.
I know. The question did it.
That was
Right. It was that green alien out front that really. While we're killing some time, Shannon and I were looking at a lot of aurora photos. There's a lot of aurora that's still going on, and there's people that are posting pictures of it all over the place. So yeah. Hi again, Naveen. Sorry. So
Yeah,
we've got
sorry.
the.
I think that's my fault because, as I said, we use Zoom Web option, and it keeps crashing.
Oh.
Problem. Hi, Naveen. I had a question about your own personal level of interest in the search for extraterrestrial life and how you think, James Webb's operations affect that.
Of course, I mean, James Webb is not designed to actually look for extraterrestrial life, right? It's only signs of, does the atmosphere of a planet have the right composition to support any life? Maybe the Roman telescope or even the future telescopes have
Right.
better chance of actually, or I don't even know if Roman telescope's goal is to find or look for the extraterrestrial life. But with Webb, no, that's not one of the questions we are going to ask. So Webb is not going to help us find extraterrestrial life. But we
I
are
would think that
making
would be-
progress in that direction. So
I would think that Webb would be useful for finding something like Planet 9, if there is,
if there
other
is, yeah.
other stuff because of the infrared use of it. It could certainly easily pick up, I would think, other planets that
Very,
could
I
be
agree.
around the sun.
I agree. Yeah. I mean, I haven't heard anything about Kuiper Belt objects because, again, these grants and they need to be approved. And whenever the scientists get the time to look at that part of the sky, I haven't heard much about Webb observing Kuiper Belt objects and finding anything new out there. So maybe it will happen if we have another 17 years of operation.
So we have the Rubin going right now. What are some of the next big, great space telescopes? Obviously, you're working on things now. I would think that the Webb is obviously, you said 20 years if we're lucky.
Yeah.
But what else is in the pipeline for you?
Oh, I mean, not here at Marshall. Marshall is mainly focus is either gamma rays and X-rays. We have some concepts on X-rays, X-ray observatories, because Chandra is probably not going to last long, and that's the only X-ray telescope that has that kind of capabilities that is in space. If we lose Chandra, US lost a big kind of tool out there. So there is one that is coming up called Lynx, LYNX, Lynx. It will be run from here. But overall, after Roman, I don't know what's the big telescope. But the good thing about astrophysics, both good and bad, I guess, astrophysics is they come up with these decadal surveys, and they decide on one big investment or one big telescope, and they go execute it. Oh, of course, it takes decadal survey back in 1990 or 2000 is when Webb was like conceptualized. It was called something else, and finally it was like 2021 we launched it. But that's in a way good. But when it comes to human spaceflight, we don't have that kind of decadal survey. That's why we keep, taking 3 steps forward and 2 steps back kind of approach for human spaceflight. So
Any other?
whatever the decadal survey that released, the latest one, should have that information about what's the next big telescope.
Yeah, here, I'll go to you, Franco. Here you go, buddy.
I got one question.
Okay, good.
Yeah, my question is, how does the kind of like field of view or of the James Webb compares to the one of the Space Hubble? How much of the sky one can see versus the other?
Webb, over a span of year, it can see the entire sky, except for, of course, it won't see towards the sun. But the Webb can look at every part of the sky, almost 360 degrees, except for looking at the sun. It always has to point away from the sun.
But my question was, if how big a picture is one versus the other? I mean, is it the James Webb much bigger than the Hubble, or it's similar, but resolution?
I think image resolution of Hubble and image resolution of Webb is going to be same, because the mirror, the image resolution, the resolution is directly proportional to the size of the mirror, but inversely proportional to the wavelength. As Hubble has a smaller mirror, but it is looking at the universe in the visible part of the spectrum. Webb has a bigger mirror, but it's looking at the universe in the infrared part of the spectrum. It has a longer wavelength. That's why the resolution of the image is going to be same. The field of view, I think it's Hubble and Webb are comparable, but I heard Roman has like 10 or 100 times bigger field of view compared to Webb.
Thank you. Who else?
I think I have one question from online. How much of Webb's observing time is dedicated to techno and biosignatures? And has there been anything found?
I didn't see any data on like particularly how much is how much has been assigned for one field of science or one particular area versus other. So I'm no longer supporting, so I don't have any internal kind of information about the mission and the project. It's all NASA Goddard. We don't have anything at NASA Marshall related to Webb. We don't support Webb anymore. We did during the assembly and testing phases, but after that our participation in Webb ended there.
Well, we're yeah, I think. Oh, we do have Jonah's got one back here. Hold on a second. Here you go, Jonah. Let's do one last one.
I was just wondering whether you knew whether either like in the past or going into the future, whether there have been like studies on the feasibility or usefulness of like refueling either the fuel or coal or cooling on especially some of the more shorter lived telescopes.
You mean just like Hubble, how we service Hubble? Are you talking about servicing Webb or like what?
Webb would be hard.
Well, Webb's much further out, but like with
Mhm.
some of the like space telescopes that use like liquid helium or other coolants, like and so have that shorter lifespan, like refueling those and servicing those.
The biggest I mean, it depends on how much money we have to support that, and the other thing is how do we manage cryogenic fluids? How do we manage transfer of those cryogenic fluids in space? We are still not there yet. Even for human space flight, we are still figuring out how to transfer these cryogenic fluids in space. The only test we have done so far was one of the SpaceX Starship launch. They demonstrated for, I don't know, 30 minutes or so. And that's the only test that we have done so far. So technologically, we are not there about on the cryogenic fluid transfer in space. We still have a long way to go.
All right. Well, let's stick a fork in that, and please give a hand to Dr. Naveen Vetcha.
Thank you. I appreciate
Thank you so
the
much.
invite.
Yeah,
and,
we hope that
fun.
we'll do this again next month, and we hope to see you here in the classroom as we have Professor Yu from Columbia will be here, and so she'll be in person. So if you're ever up in town, make sure you look us up. It would be great to meet you, sir.
Yeah, and same invite. I extend that to you all. Come down if you ever come down to Huntsville, Alabama. Check out our Von Braun Astronomical Society. I was past president, and now I'm the outreach coordinator for last 8 years or so. We set up telescope schools, Space and Rocket Center, wherever in the state parks and all that. Unique history. We just celebrated in October 75th year of our formation by Von Braun and his German team. Even before they started in NASA, they started our observatory and telescopes and all that. And they used the telescope here to scout the landing spots on the moon for Apollo. So pretty unique features. Even our dome, the planetarium dome, we call it lovingly unique planetarium dome in the observable universe, because it's not a standard planetarium dome. It's when they were building Saturn rocket, stage 2 and stage 1 and stage 2 are being built at different locations, one in California, one in Texas, just to make sure they can, mate properly. They built a dummy bulkhead for that tank. And then once the Saturn program was over, that dummy bulkhead was like sitting in trash at NASA Marshall. And when they decided to build the planetarium, Ron Brown said, let's use that as a planetarium dome. So it's that's the planetarium dome that we have. And we use the Spidge projector from 1960s, very unique, and very few such planetariums are left. So I can relate with you all. So come down if anytime. I will be happy to.
Yeah, thank you.
Yeah.
That really sounds like pretty amazing. Yeah, I love that.
Yeah.
Thank you.
Yeah.
Thanks again, Doc.
All right. Thank you.